University. He has published over 500 papers in high-end computing and networking. The MVAPICH2 High Performance MPI and PGAS over InfiniBand, Omnipath, IVARC, ROCE, and EFA libraries, designed and developed by his research group, are being currently used by more than 3,200 organizations worldwide in 89 countries. More than 1.54 M downloads of this software have taken place from the project site. So this software is empowering several InfiniBand clusters, including the 4th, 13th, 26th, and 38th ranked ones in the top 500 list. MPI-driven solutions for providing high performance and scalable deep learning for TensorFlow and TensorFlow frameworks are available from the Ohio State website. Solutions to accelerate big data applications are available from the site hibd.csc.ohio-state.edu. Professor Panda leads one of the recently funded NSF AI institutes, ICICLE, to design intelligent cyber infrastructure for next generation systems. Professor Panda is an IEEE fellow. More details of Dr. Panda are available at www.csc.ohio-state.edu/Panda. With this brief introduction, I extend a warm welcome to Professor Panda and hearty welcome, sir. The stage is all yours.
Okay. Thank you. Good morning, all of you. Thank you, Dr. Shriram and Mr. Ganeshan, for inviting me to share some of the things what we have been doing in my group for the last almost 25 years. So I'll try to give a very high-level perspective of where this high-performance computing field is heading, together with machine learning, deep learning, AI, data science. So this is where the field is going. So how do you design software or middleware for these kind of systems? What are the challenges? What are the opportunities? And what kind of performance also you can get on current generation systems? So as I proceed, if anybody has any questions, please feel free to post it in the chat. I'll be monitoring the chat, and then I'll also be pausing in between, and then we'll be trying to answer these things. Sorry. So if you take a look at the current and next generation application, whatever is happening, there is a significant growth in high performance computing. So over the years, last several years, if some of you might be knowing what is happening, there is a significant growth in processor performance. And that performance is coming not because of the clock speed, but rather more in the chip density. So chip density has been doubling every 18 months. So the very latest one, if you take a look at from AMD, their Milan system, it has 128 cores within a node. So imagine in the next few years, you will have a laptop with 128 cores. It will be a very powerful computer in front of you. So the question is what you can do with all those computing power. So it is not only just one node, but imagine connecting 4,000 or 8,000 of these nodes, and that becomes a supercomputer. So that is where the field is going. But now let's say I want to connect this kind of 4,000, 8,000 nodes. What will be the network? What kind of network should I be using to deliver this kind of the performance? And this is where a lot of growth is happening in terms of commodity networking. There is continuous increase in speed, features, and at the same time, since these are commodity, just like you go and purchase a TV or a refrigerator, these days you can actually go and purchase the servers. You can purchase the networks and put together your own system. So this is where a lot of companies are competing with each other to reduce the cost. And this is how the clusters are being designed these days. If you have a lot of money, you can actually buy commodity servers, commodity networks, commodity storage, put them together with some open source software like MVAPICH2 I'll introduce from my group, and you will have a supercomputer ready. And using that, you should be able to run not only your high performance computing application, deep learning, machine learning, data science, all kinds of AI applications also, yeah, you can run. And that has become a popular choice to provide scalability, modularity, and upgradability. So here are some examples, like let's say, think of like a company like Ford or Honda or Toyota. They do a lot of like car simulation, crash simulation. So that is requires a lot of computing power. Similarly, like a nuclear simulation, bioinformatics, all these applications require a lot of computing resources. So while we are focusing on computing, there is also a lot of need on the data. The world is exploding with big data. If you see a lot of these such examples, now people are trying to understand, process those data, and then trying to make sense out of it, because there is so much data is being generated. You need to really see how to process them, what is the trend, how can we learn from those data. So all these big challenges are coming. So that is leading to a new field called high performance data analysis, or HPDA workload. And they are not only being running on the regular clusters and supercomputers, there is also they are also running on the cloud. So we need to keep both these kind of systems in mind as we move along. Now let's take a little bit more concrete example of some of the grand challenge high performance computing applications people are exploring. So think of this very simple example. People are trying to understand how our human body works. Okay. And especially one such example, especially to understand the heart diseases and how the heart diseases get formed over the years, people are trying to understand the blood flow pattern. Okay. Now the question is, can I actually simulate the entire human body, the blood circulation parameter? If you take a look here, it says like our body, a typical body, a heart, pumps the entire blood supply. We have 5 quarts of blood, and it goes through 60,000 miles of vessels within our body. If you put all these together, it has 60,000 miles of vessels. So the question is, can we actually try to monitor how the blood flows? If I get some medicine, how it interacts over a period of time, if how the new kinds of diseases get formed. If we can actually solve these kind of problems, it will help us a lot in understanding. You can actually simulate a lot of newer kinds of drugs. Currently they are being given to the patients. They are being tried on, like you must have heard of this all COVID phase 1, phase 2, phase 3 kind of a trials. But instead of really trying it on the human beings, you can actually simulate these things on large supercomputers. So then in that case, your drug discovery time will be much more faster. Similarly, let's say earthquake. This is an example of an earthquake, but you can think of like a cyclone, or think of hurricanes. People want to see what will be the impact. Okay, if a hurricane comes or a cyclone comes, where exactly it will be hitting. And if we can know that very quickly, then we should be able to move the people from that area to an upper areas, or take them to safe areas. So then you will save a lot of lives. So this is also another example where you need a lot of high performance computing. This is an example which is trying to show flu pandemic, like the COVID, what we are seeing these days. I mean, all of you must be hearing about this Omicron thing. How does it get spread it? Because this is a big concern for public health in any country. As you must be hearing about the news, every day you see, okay, nowadays this has increased. So people have come up with a model, like this is United States, starting from a day 1 and density of the population. Can we actually model and see, okay, what happens after 10 days, what after 20 days, 30 days, 45 days? And that helps the public health officials and government officials to plan ahead and trying to see, okay, where to send the vaccines or what kind of actions to take place. So these are like a purely computation intensive applications, and we need huge computing powers to solve these problems. But then this has been there. I mean, high performance computing is nothing new. It has been there for almost 30 years. People have been working on all different kinds of technology, hardware, software. But now we are entering this new field of AI. And if you take a look at the AI, this is a very broad field. AI has been there for also like almost 50, 60 years. But the problem was that AI had a lot of concepts, but people were not able to solve those things. Okay, people had neural networks, people had all the different models, but the technology was not there to really solve those things. But now, for the last, I think, 8 to 9 years, this field has totally changed. And this is where the new kind of machine learning, deep learning paradigms have come. And here, if you take a look at like a machine learning, we have a set of inputs. The question is, can we do some feature extraction and come up with a classification? And then if we can come up with that classification model, supervised or unsupervised, I'll go into a little bit more details later on. Now, if I have the model, then there is a new input or a new car picture comes in, my model should be able to classify whether it is a car or not. Now, that field also has been there for many years. But again, the problem was the same. Like, people are not able to solve on the using the current generation systems. Now, from the machine learning, now we have moved to the deep learning, where instead of a human involvement, we are trying to combine both this feature extraction and classification into a single step. Okay, so that means giving a lot of data. As I said in the earlier slide, these days a lot of data are available. Whether you are going through any banking organization, or you are searching for Google in the behind the data centers, there are a lot of ways to collect data. And if we can take those data and try to learn, the question is, can we come up with a better models, and we can try to automatically, the machines can actually try to do similar kind of analysis, what the machine learning used to do with some human intervention. So let's take a very concrete example of credit card fraud detection. Okay, so this is very important. I'm sure many of you have the credit cards. These days, as the credit cards are becoming very widely used, suddenly, let's say you lose it or somebody steals it, he or she is trying to, the thief is trying to utilize it at many places. So how quickly a bank can determine that there has a fraud has taken place? If there is a very real time scenario, if you wait for longer time, the thief is trying to use that card at many different places, and then the bank is responsible for all those lost money. So in this context, the community has developed like a fraud detection using machine learning. Here you can see like there is a model, and using that model, there is typically a prediction. Okay, for example, if I take like my credit card, mostly might be I'm using in US, and this I have seen actually in the past. Sometimes I try to, when I visit India, I try to purchase a ticket on Indigo Airlines or something. I give the credit card. All of a sudden, I get a call from my bank saying somebody is trying to utilize your card in India. Okay, even though I am purchasing, but the transaction is taking place in India, so the bank actually detects this using this kind of model, because they have the prediction that mostly my credit card will be used in the United States only. So if I deviate from that, then all of a sudden it triggers. So this is where they try to predict. They have some explanation. There are some human, like the bank personnel are involved, and then they call me so that they can try to very quickly detect whether the fraud is taking place or not. Again, this is an example, but behind the scene, here you'll see that there is a huge amount of computing power, again, you need to solve these things. But since this problem is very, like really deals with money, as you can see here, it says in US in 2019, almost 112 million was lost due to credit card fraud. So the banks are very sensitive about this. So now they have been investing a lot of technologies, hardware, software, and solutions to detect this quickly and then try to save that. Not only like they are trying to prevent the loss, they are trying to help the customers to make sure that even if your card gets lost, you are able to suspend that with a very short period of time. Then so that is like a machine learning where human beings are involved. Now let's take an example of deep learning. And the deep learning, as many of you know, is very widely being used these days. I'll go through some examples here. So think of this example. So this example is trying to show how we can try to mimic or learn from famous painters. So let's say Van Gogh. Van Gogh has been a famous artist, and he has a typical style. So the question is, can we actually teach a machine or a computer to learn those styles? So that means if I give some doodle, the machine will actually draw this or paint this picture as if Van Gogh would have drawn it. Okay, I mean, this is very complex task. Okay, as you can see, like there is a science and engineering, there is an art and creativity, which is very complex, and it totally depends from person to person. The way I can paint is very different than you can paint or a big artist can paint. Now, of course, there are some other issues like ethical issues. Is this good or not? That is a different story. Of course, in the AI area, a lot of people are working on ethics and all. For the time being, we'll not focus on that. We'll focus purely on the technological capabilities and then the achievements. So then here, if you see like these examples, like a, let's say, simulation of the aircraft, all the different parts. Many years back, if some of you remember, the airplanes were being designed and being evaluated in wind tunnels. I don't know how many of you remember this or would have heard of it. There used to be really wind tunnels. There is a small clay model of the aircraft used to be there, and then they actually pump the airs and then see whether the components are working or the flight is stable or not. But these days, everything has become simulation. So if an airplane has like a 50,000 parts, each and every part gets simulated, and then you put them all together and then try to simulate this entire aircraft and then see whether it works or not. And if it works, you directly go and build it. In fact, Boeing switched to this kind of designs, I think almost 10 to 15 years back. And Airbus is trying to do the same thing. So that actually cuts down your design and development time for the entire aircraft. Now, this has been happening, but now what is happening is these simulations are going to the next step, which is like AI-driven simulation. So what does that mean? So let's say I have 50,000 parts. Of course, I mean, there are all combination. Let's say each part has like a 3 stages or 3 different parameters, which is very simple. Typically, these have like a 10, 15, 20 parameters. Your complexity of the simulation grows in a big manner. Okay, with 3 parameters, I have 50 parts. You have to do 50 times 3 kind of a simulation. Okay, so this is a huge complex simulation, but the thing is all those simulations don't lead to good results. So this is where the deep learning or AI comes in. While the simulation is running, can we actually also monitor the results? And if we know that in the past run, this set of parameters, this combination didn't lead to any new results, I don't have to run that. Okay, so that means we are using AI or the deep learning to learn the simulation patterns and then try to cut it down. Okay, so even this simulation, let's say earlier it was taking 1 month. Now with AI driven knowledge, we should be able to even reduce to 10 days. So that means that will have a significant impact in the overall design and development time. So these are more complex examples. Even simpler examples like these are also very helpful. I mean, if you go to another country, especially in Europe, even though like let's say I go many times there and I try to purchase some cookies for my daughter. Every country has their own languages, and I don't know all the languages. Not only that, I also don't know the ingredients. I just want to make sure that the ingredients are correct. So I can just use a very simple Google Translate. Okay, Google Translator, I can just use this, and then irrespective of the languages, it comes back and tells me, oh, this is a dark chocolate. So then I'm happy, I just purchase it. So you can see that I'm trying to show the complexity of the deep learning and AI from even the big airplane simulation to even to detection of the languages on a cookie box. Okay, so people are trying to utilize this kind of knowledge in all these areas. And of course, the biggest challenge is self-driving cars. This is the kind of a pinnacle of deep learning. If you must be hearing, like cars like Tesla started all these things. It's a driverless car. And gradually, I think in many places in the world, these kind of vehicles are already coming. It is able to detect. It has a lot of sensors. It has a lot of cameras. On real time, it is able to actually get those knowledge, and then trying to identify that, okay, should I be stopping? Should I be making a right turn? Should I be taking a left turn? And if another car comes in front of me, should I be putting brakes? So all those kind of things, automatically the car is able to do it. So a lot of progress has happened over the last several years. It is not 100% perfect yet, but the field is moving into that direction. Another example is AI-driven medicine, or AI-driven, in this case, a digital pathology. Okay, so it's a very common case. Anytime, like as we fall ill, we go to doctors. Doctor prescribes saying, okay, we'll be taking your blood specimen or some tissue specimen. We'll try to analyze it. So we give that. Then in another two days or something, we hear back. Okay, and so typically what happens, you take these kind of images, which are very large images, and then the pathologists, which are very have been trained over the years, are able to very quickly identify, saying, look, there are some issues here. Okay, so in this case, they are able to detect, like, oh, this is a breast cancer. Okay, now the question is, these pathologists have been trained over the years. Okay, so even though like a pathologist takes like a 10-15 minutes, they're very expensive. Okay, and it also goes through a lot of steps. So the question is, can actually machines try to do this kind of diagnosis? Can deep learning be used to help? Okay, I'm not saying that the entire machine will be able to give you an yes or no answer. I don't think everybody is ready for that. If somebody, if a doctor tells me that I have a cancer, I'll believe. But if a machine tells me that I have a cancer, I'll have some doubts. So I'm not saying that. But the question is, can the machines actually try to do some pre-processing, or rather narrow down the thing? Because in the hospital, over the years, they have so many images, millions of images. And can they take actually those images, try to do a deep learning on top of that, and then if a new image comes or a new specimen comes, they can actually compare it. They can have their model design, and they check with that model, and then they can have inferencing saying, okay, there could be a probability that this kind of diseases could be there. So in that case, the pathologist who was spending like earlier 15 minutes, might we can try to do this analysis now with 5 minutes, because the machine actually has helped to narrow down the choices. So in that way, actually, the end customers, like the patients, get a very good turnaround time for their diagnosis, but at the same time, the healthcare cost also goes down. Especially in US, the healthcare cost has been rising over the years. The doctors, the pathologists, everybody is so expensive these days. Okay, so there is a big push, also trying to bring now to the AI to the medicine field. So if you take a look at this broad AI, where we are heading, these are some market trend I'm trying to show, and some use cases. So market trend, if you see here, this is just the AI revenue, the world markets. We are here like a 2021, we are almost finishing. It is a $10 billion market. Now, just in another 5 years or 4 years, they are predicting it will go to $36 billion market. Okay, so this is where all the fields are actually heading into that direction. And in the right hand side, it is trying to show some of the top 10 markets where AI is taking a big taking a lot of big trend. I talked about some of them, but here if you see some more examples, like contract analysis, object detection classification, geospatial images, tracking from geospatial images, geophysical feature detection, text query of images, content distribution, predictive maintenance. This is actually also very important. Even in a common man, think of like a cars. I mean, the cars typically, currently they are being maintained in a particular time, or so many miles or so many kilometers you have gone, then you need to do a maintenance. But actually, when you go for the maintenance, obviously we do those things, but it may or may not be needed. It totally depends on how the owner has driven that vehicle for in the past, on which roads they were used, or in which cities they were used. So the answers will differ from situation to situation. So here the question is, can we understand that behavior? So in that case, we can actually try to make sure that, oh, this car has been driven in the past. These models tells that okay, for this car in this city, there is a very high probability that this component will fail in the next 15 days. Okay, so if we can identify that, then it is better to go and fix those things before it actually your car breaks down. Okay, so that saves a lot of not only money, but also saves a lot of resources, and it also helps a lot of passengers. So same thing is happening with respect to, not I gave an example of cars, but same thing is happening with the trucks, with buses, with airplanes. So a lot all transportation mechanisms, people are spending a lot of money and effort to understand this predictive maintenance. Patient data, I gave an example of the pathology, static image recognition, classification, tagging. This is the whole world, our World Wide Web. When you do some search, are you able to get the correct thing? Okay, so that totally depends on how the images and videos and audios have been classified, have been tagged. And of course, the end one is the topmost use case is the algorithm trading strategy. In any stock market exchange, there's a lot of money involved. Every day stocks are being sold and purchased. So the question is, can actually a deep learning model be developed so that it can actually predict based on the factors happening in the world, based on happening whatever the all other factors, it should be telling that, yeah, tomorrow the stock may go down. So in that case, it's better to actually sell before that is kind of a holy grail. So that's why you will see a lot of money is being spent to understand that kind of a market. So here, these are some of the examples I just provided just to motivate you to see where, when we talk about HPC, AI, and big data, where they are actually being used. So we'll keep that in mind for the remaining part of the talk, so that we can actually correlate things. Are there any questions so far? If you have any questions, please feel free to post it on the chat. I am monitoring. Okay, no questions so far. So let me proceed, and please feel free to post it, and we'll discuss that. So now since we know the applications, now let's see what is happening. How do we design these systems? Okay, so this is where I'll like to introduce the high-end computing systems. Okay, and this data is taken from a list called Top 500. I don't know how many of you are familiar with Top 500. So Top 500 indicates the top 500 supercomputers in the world. Okay, so every year, twice every year, all the supercomputers in the world are ranked. And of course, this is the global ranking, and I think there are also regional ranking. Like for example, I think within India also there is a top, I think top 50, if I understand, top 50 or top 20 supercomputers within India. So like this, every region has their ranking. But here I'm trying to show the top 500 in the world. So x-axis is actually the years, and the y-axis is trying to show their performance. Okay, and the performance is actually this is a log scale. So even though some of the line looks linear, but it's actually exponential. So the measures, these supercomputers are measured in terms of flops, like how many floating point operations they can do. So here what happened, like the petaflop, we crossed this petaflop range many years back. In 2017, we crossed 100 petaflops. So okay, that was like a milestone saying, can the machine actually deliver 100 petaflops? Then within 3 years, we moved from 100 petaflops to 442 petaflops. Okay, so that is the system in the Fugaku in Japan. So that now actually delivers, it has 7.63 million cores, you can see. So 7.63 million cores on a single system, and is trying to deliver 442 petaflops. That still remains number one in the world so far. And then we'll try to see whether there was a discussion that this last November, when supercomputing conference was taking place in Europe, in US, people were talking that might be some exaflop systems from China will be announced, but we have not seen that yet. So that was not announced. So this is where the field is, people are waiting to see whether.
Sorry to interrupt, Professor Panda. I think you are there in the presentation view, or the presenter view.
Something got changed?
No, the presenter view, it is not in the full screen. It is showing in 2 screens. Yeah. Hide presenter.
Oh, really? Okay.
Hide presenter view. Yeah. Hide presenter view.
Okay. Is it better? No.
It's showing all the screens. You may just go to the slideshow. Resume.
Yeah.
Yeah, that's it. Can you please click on that, sir?
Yeah. I think just let me stop sharing and then come back. Sorry for the problem. So,
no issues, sir. No issues.
So from the beginning, you were not seeing the slides or just?
No, we were seeing the slides, but in this graph, the size of the letters.
Oh, I think so. Something got disturbed here. Okay. Okay. Sorry. Let me. Are you able to see now?
No, sir. Where it is.
Okay. I believe something happened on my. Just give me 1 minute. Let me try again. Just. One minute, I think. I'm trying to open up the slides again because it went away. Can you see it now?
Yes, sir. Yes, sir.
Okay. Sorry.
Perfect, sir.
Yeah. So let me just. Do you see something corner? Something? I can close that.
Nothing, sir. It's perfect now.
Yeah. Okay. So this is where, like as I was telling, this is the number one system, and now of course the community is waiting for the exaflop systems to come. So the exaflop is actually 1,000 petaflops. Okay. So we are still not there. If you see, like in 4 years, we came to 442, and people are mostly expecting that the next year, 2022, we'll be actually seeing 1,000 petaflop system. Okay. And so this is where a lot of excitements are taking place in terms of the computing platform, networking platform, storage platforms, to see how we design the systems, and not only just design, how to use those systems. Okay, so that is also becoming important. So now let's take a look of some data. Again, I'll be trying to use some of the top 500. So as I said, you can actually utilize, you take these numbers or go to this website. You should be able to get these numbers. They have a very nice statistics collection. So here, what I'm trying to show, what is the trends for commodity clusters? I think I introduced that commodity cluster earlier in a qualitative manner, but now let's take a look at the quantitative manner. Okay, so here it shows, like, the x-axis is again over the time what has happened. The y-axis is out of those 500 systems, how many of our commodity clusters. That means if you have money or if you have a budget, when I say you, whether an individual or an organization or a country or a state, whoever has some money, can they actually go buy a bunch of servers, go buy a bunch of networking gears, buy a bunch of storage, and get some open source software, and then put them together, and can it work like a supercomputer? So that's what we are considering here. So if you see, in the very old days, it used to be like these used to be the proprietary systems. Okay, like the traditional Cray connection machines. These are some of the older architectures. Then in the early 2000, things got changed, and now if you see the latest ranking, it is 98.4% of the systems are commodity clusters. So that means these days you can actually design these systems very quickly. Okay, and I believe, like, there are a lot of examples like this in India also, and I believe, Dr. Shriram, you have a lot of systems within Shastra University, am I right? These are commodity clusters. So these commodity clusters, actually, if you go inside, this is how it's designed. It has a set of multi-core, many-core processors, some high-performance interconnects like InfiniBand. It has become very common over the years. I'll refer to that many times throughout the talk. Accelerators, whether it could be GPUs from whether it's NVIDIA or AMD or Intel. And then, of course, you have some storage. And then you put them all together, you have a large supercomputer with you. And this is how it is happening. Whether you have the number 1 Fugaku or number 2 Summit, Sierra or Sunway, Twilight, any of these systems are actually trying to follow very similar configuration. And the processors could be different. For example, Fugaku is ARM, but Summit is actually open power. That's how it's the number 2 system in the world now. It used to be number 1 earlier. The Sierra is also open power. Sunway, Twilight from China, they have their own domestic processors. Okay. So in this context, when you try to design software for these systems, I gave all these examples earlier, like the purely high performance computing, deep learning, machine learning, big data, data science. So there is a very nice convergence is taking place. Okay. In some of the examples I indicated earlier, not only you need the raw computing power, you also need to have capabilities to analyze big data. You also need to have capabilities to run deep learning model on top of that or machine learning model. So a lot of newer kinds of frameworks are emerging. And in those frameworks, you need to make sure that the underlying software stack actually helps the end user to run all these different kind of applications. So that has been actually the focus in my group over the last 20 years. So here, especially, I'll try to focus on gradually introduce MPI, which is the MPI is the message passing interface standard. It has been there for almost now 20 years. So that provides a parallel processing on any of these large clusters. And traditionally, API people had only thought for high performance computing. But I'll show you some results here that just using the same MPI library, you should be able to actually handle all these kind of applications or the use cases. You don't need many different kinds of middleware or software. Just MPI's library will be good enough for you to run all these things. And not only on your local cluster, the similar things can also be used in the cloud. I'll also try to show some examples there. So then the question is, how do you design these communication libraries, or let's say the MPI libraries? So typically, I'm sure many of you must have heard of this term called programming models. Okay, so when you do a parallel programming, there has to be some kind of a model which you are following, and that model reflects how a process communicates with each other, where you do communication, where you do synchronization, where you do I/O. So depending on all these use cases I indicated, MPI can be a programming model, TGAS, which is a partition global address space, or even the CUDA, which is for GPU, or OpenMP for big data, Hadoop or Spark, or even for deep learning, TensorFlow or PyTorch. Any of these could be your programming models. Okay, so typically users keep that in mind when trying to write a parallel program. But then if you see at the bottom, I call like the supply side. That means all these different kinds of multi-core, many-core architectures from Intel, AMD, accelerators, GPUs, FPGAs, different kinds of networking technologies like InfiniBand, Ethernet, Rocky, Omnipath. There is a new networking which is being proposed by Cray and HPE called Slingshot. So all these technologies are coming. So I identify these like a supply side. So that means these technologies are coming. They propose a lot of newer mechanisms, newer features. And the question is, how do we take those features and mechanisms and really help the end applications which are sitting at the top? So there is, of course, we need to bridge this gap. So here, if you see, there is a typical application kernels use middleware. Middleware actually use those programming models. So this is where your communication library comes in. Okay, so the idea is that how best I can do point-to-point communication. Okay, because that will affect the performance. Okay, how fast I can send data from one node to another node, host to host, or GPU to GPU, GPU to host, all this point-to-point communication. There's a lot of focus on collective communications, because a lot of these applications, both scientific as well as machine learning, deep learning, use a lot of collective communication like all reduce, okay, or reduce, all to all, broadcast. So if you can optimize that layer, you will be able to accelerate all your applications. Okay. Similarly, you need to design these energy awareness, synchronization logs, IO file system, fault tolerance. So this is where the communication libraries roles comes in. And these kind of designs can be done in a layered manner, or you can also try to do co-designing. That means you make some changes to the model, you make some changes to the library, you make some changes to your hardware. And then when you put them together, you actually get even better performance. Okay. And even including application also. And this is what has happened over the years. A lot of co-designing has happened to deliver even better performance, scalability, and resiliency. So keeping this big picture in mind, I'll actually go through this will be kind of the different parts of the talk. I'll start with the MVAPICH project, that is the MPI library. Um, we have been working almost for 20 years. I'll try to show you how we have done this design using pure CPU, also with a GPU. Okay. And then there is a new technology which is coming, some of you must have heard of, called DPU, data center processing unit. Okay, so that is giving us, in fact, newer ways to design these systems. So I'll give some examples. So these are all the projects in my group, and we have a lot of software which we have developed over the years, and these are available and publicly for people to download and use all those things. So then I'll go into this HighDL project, which is high performance deep learning. So I'll try to cover how using that MPI driven solutions, you can actually carry out high performance deep learning, machine learning. Then I'll go into this big data. We call it HighBD, high performance big data project. In addition to accelerating like the traditional big data stacks, like Spark, Hadoop, recently we are focusing a lot of data science applications. So there is a middleware called Dask, and I'll try to show you how you can actually accelerate Dask on your system. And these components are there individually. One can actually download and use these. And we have been recently, as you know, the field of cloud computing is becoming very common. A lot of people want to run in the cloud. We have been working together with three major cloud providers, AWS, Azure, and Oracle, to have actually our software stacks being deployed there. So that means if you are trying to utilize or rather go for a cloud option or your on-premise option, you should be able to utilize our software stack and then develop your applications in a very transparent manner, whether it is in-house um, uh, or on the cloud. And all these research have taken place from the Ohio State University side. Um, but over the years, there have been I've received a lot of requests because a lot of people have been using our software stacks to really provide commercial support and value-added products. So that means whatever is available from the OSU side, they want more optimizations, more enhancements, more newer features. So I'll be talking a little bit about that and then conclude the talk. So let's start from the MPI side. As I mentioned earlier, I mean, when you are trying to design supercomputers, so take an example of Summit. As I indicated, which is currently number 2, but it's a number 1 system earlier. It is built with open power. It uses InfiniBand. So broadly, you will see it has 4,000 nodes, okay, with open power. How do you connect and then 4,000, and then it has, every node has 6 GPUs, so 24,000 GPUs. So how you can design an MPI library which will coordinate a task, a parallel task across 4,000 nodes with 24,000 GPUs, and in fact the number of CPU cores is very huge on this system. 4,000, I believe. In every node, I think dual sockets, 32 cores each. So 64 by 4,000, almost 250,000 cores. Okay, so it's a big, massive effort you need to take care. So within that library, this is where you try to see like you need to provide this kind of a scalability for million to billion processors. You need to, these are like a point-to-point communication. You need to achieve all this collective communication, and especially when the number of cores per node, as I indicated earlier, like 128 cores per node are available these days with Milan, and very soon we'll see 1,000 cores per node. So imagine you are connecting a bunch of nodes with 1,000 cores. A lot of communication happens within the node, but at the same time, a lot of parallel communication happens across the nodes. Okay, so how do you really design the balance, this intra-node and inter-node communication? So in that context, you may need to support for some efficient multi-threading. You need to also provide some good support for GPUs, accelerators, fault tolerant, quality of service, virtualization, etc. and etc. So those are the kind of the very big effort you need to put together to make a complete MPI library ready. So, and this is what we have been working in my group. We started this project called MVAPICH. We started this project almost the day one of Infiniman. Infiniman technology was introduced in 2000, almost 21 years back in October 2000. And prior to that, in my group, we are working on the older networking technologies called Mirinet, Quadrix. Only some of the senior people might be remembering those names. And when Infiniman came, we were the very first one in the world to jump in and really design a MPI library which can take advantage of the Infiniman interconnect. Okay? So we had our first open source version, which was demonstrated at Supercomputing 2002. Within 1 year, we had a complete design ready. And then since then, we are continuously evolving. Even though it was originally for Infiniman, now we support all the different networking technologies, all the different platforms, CPUs, GPUs, and also DPUs. We also have been continuously upgrading with the MPI standard. We are actually a member of the MPI standard. We contribute to the MPI standard. So over the years, this library is now currently being used by more than 3,200 organizations in 89 countries. And these are only registered, voluntary registered organizations. A lot of people actually download with Gmail, Hotmail accounts. They don't want to identify their organization name. That is okay with us. Just from our OSU website, we have actually crossed 1.5 million downloads. Okay, 1.5 million downloads. And that is directly from our OSU project site, but the software is also available with a lot of other stacks, Red Hat, SUSE, OpenHPC Stack. If you download a Red Hat disk, you will see our software is there. It is very hard to keep track of the secondary, tertiary downloads, but that is a huge number, even compared to what the direct download takes place from our site. So it is not only just the download, we have been empowering a lot of these top 500 clusters over the years. Every time some new large clusters come up, many MPI libraries don't work. So actually they contact us, we work with them to try to make sure that it goes to the next level. So here you can see like just a release download tables. As you can see over the years, especially in the last few years, we are on a steady rise. Every day we have several thousand downloads taking place for our website. So this is like the overall architecture, okay, so which we have been continuously evolving over the years. At the bottom, we have support for all the different networking technologies. Right hand side, we have support for all the different multi-core, many-core, GPU, DPU architectures. So this is where in between we design this runtime, and in the top, we provide the interface for MPI, PGAS, and hybrid MPI plus PGAS. And through these interfaces, we not only support HPC, but we also support the deep learning, machine learning, and data science. That's what I'll be trying to show in the next set of slides. So we call it like a MVAPICH2 software families. There is a base version. There is a little bit advanced version we called MVAPICH2 X, like the next generation. And then there is another version which is very much optimized for GPUs. And also it supports all the deep learning and machine learning. So I'll try to primarily focus on these three versions. There are some other versions like for cloud, energy awareness. I'll not be talking about that more. I'll just focus on these three. So typically, since we are a university, many times what happens, our approach is very different than any other industry. Okay, because many times in the industry, you know, like they just go and come up with a solution. So the question is that solution optimal? The answer may be no. But what happens within every time, like we have a new opportunity, just like I said, some new technology comes, whether it's a multi-core or GPU or networking technology, we first try to do research and then study it very carefully. Might be we have 5 design alternatives. From those design alternatives, we try to find out which one is the best. We publish those papers, and then 6 to 9 months, we take those designs and then really push it into our MVAPICH2 library. Okay, and we go through very rigorous testing, just like any other company. In my lab, we have almost 200 servers continuously doing testing 24/7. Okay, so that we need to make sure that the code is very stable, code has performance. We do a lot of performance regression, just like any other company. Okay, and then when we make the release, you can actually download and try to run it on your system, and directly you see the performance. So that is the kind of the ecosystem we have been maintaining for the last 20 years. So now let me go into a little bit more details just to give you a feel. Okay, each and every concept actually covers multiple papers, so I don't expect each one of you to understand each and everything, but I'll just try to give this because many of you are students. I'd like to give an example of how the research gets done in this area. Okay, so I'll go through some of these things one after another. Okay, so here this is a paper we published. It was published in Supercomputing 2018. It got a best student paper award finalist. So the problem was like this. So as I indicated, like every node these days have a lot of cores. Okay, so think of like AMD Milan, it has 128 cores. So when you run MPI, you have 128 MPI processes running within the node. So how quickly they can communicate to each other. Okay, if I can optimize that, because many times, for a parallel application, the communication becomes the bottleneck. If I can accelerate the communication, it can make the communication overhead very low, then I'll get very good performance and scalability. So here, one example, if you see, the concept here is called cooperative rendezvous protocol. Okay, if some of you are familiar with MPI library, how they get designed, there are broadly two protocols. One is the eager, which is for a small and medium messages. I just copy it to a buffer and then send it. But for large messages, if I want to send, it goes through something called a rendezvous protocol. That means if I'm a process and you are a process, I want to send 4 megabytes of data, you may not have memory buffers your side. So to handle it, I typically send a request to send RTS. You post your buffer, send me a CTS or clear to send, and then I send the data. Okay, this kind of design has been there for many years. What we try to see that for very large messages, it is taking a lot of overhead because I need to send an RTS, CTS, and then do the data transfer. So we try to explore, can we accelerate it better? Okay, so the concept we came up with is called cooperative protocols. Okay, so let me give you a real life example, and then you can understand that. Let's say you have a friend who is staying in another city, might be, let's say, 100 kilometers apart, and you need to send something to your friend. So there are two alternatives. Either you drive or go in any transportation mode and give the package to your friend and then return back, or your friend comes and picks it up. Okay, so if it is an 100 kilometer, when you go 100 kilometers and come back, you are actually spending 200 kilometers, like your time to take care of this task at 200 kilometers. The same thing happens for your friend. But there is an other alternative. Can both people come in the middle? Okay, like I go 50 kilometers, my friend comes 50 kilometers, and then we do the exchange, and then we return back. In that case, you will see everybody will encounter only an overhead of only 100 kilometers, not 200 kilometers. So that is the kind of concept we actually put it into this MPI protocol. Okay, and now suddenly you saw in this paper, you can see we were able to give you almost 2x improvement in large message latency and bandwidth. And here you can see some of the applications like Graph 500 or COMD, MiniGhost. We are able to get like a 19%, 16%, 10% application. It's exactly the same hardware. And people were thinking in a particular manner over the last 20 years, but we changed the direction. And once this paper was published, we pushed our results. And during the last 3 years, all other MPI libraries have copied this concept. Okay, now you'll see other libraries also claim the same thing, but the ideas actually came from our lab. Similarly, another example here, if some of you are familiar with InfiniBand, as the system size becomes larger and larger, the question is, what transport protocol do I use? Okay, so typically there has been something called a RC, which is reliable connection. That means if I want to talk to, or I want to exchange messages to 100 processes, I have to establish 100 connections. Okay, it takes time, and when I send the data, it also has some overhead on the network adapter. So Mellanox is the InfiniBand designer. Now they are a part of NVIDIA. They introduced something called the direct connect transport, but nobody had really studied the benefits of that. So this was the very first paper we saw that if you use this DC protocol, we're the very first one again to bring that DC protocol into our MVAPICH2 library. Now you see, compared to the basic MVAPICH2, this feature is available in the MVAPICH2 X, which is our advanced version. You can reduce the execution time by 76%. Okay. So once again, if you try to handle this kind of advanced designs properly, you should be able to really get boost to your application performance. So you can actually try to see here these numbers we have taken. We have been working with EPFL, that is the Switzerland. They have a very large problems building brain circuits. So they try to do brain simulation, and they suffer terabytes of data. So on their system, we have been able to actually deliver this kind of performance benefit. So like this, I'm just giving some samples. Of course, there are hundreds of designs we have done, but then the end, you need to put them all together. Okay. So I'll try to show some numbers on platforms since it is an open power workshop. Let me start with some open power. So here you can see we are comparing MVAPICH2 with Spectrum MPI. So this is a Spectrum MPI which has been from IBM. And as you can see, this is like a small message latency. That means the time it takes to exchange a small message. This is intra-socket. So that means if two cores are within the same socket, as you can see, using our cooperative protocol, we are able to deliver far better latency compared to Spectrum API. Large messages, here it is similar. Bandwidth are also similar. Here we see we deliver better than Spectrum API. Here we are trying to show like a similar kind of the small message latency. These are internode. Okay, so here is the internode. These are connected with InfiniBand. So here you can see, like for some cases we even lose a little bit. Like a internode, we lose it a little bit here, but in some other cases we are actually able to deliver better performance. This is on the very latest AMD Milan system I've been mentioning. Here you can see, look at this number. This is with our latest release. So this is actually 190 nanoseconds. Okay. In fact, there are two cores within the same socket. We are able to do MPI exchange of data, short messages using 190 nanoseconds. Okay. And then the bandwidth, the rate at which you can send data between again two cores, goes to almost 42 gigabytes per second on the same node. So all these things, we are always trying to really take the MPI library to bare metal performance. Okay. So whatever the hardware can do, we put only very little overhead on top of it and give you that kind of an MPI programming model, so that if you have an MPI application, you should be able to really get very good performance and scalability. Here, these are some of the numbers with ARM system. So here again, this is the similar like a ARM processors as being used in the Fugaku system, but this is with InfiniBand. So there is a system in the Stony Brook University here called Ukami. So here we are comparing an MVAPICH2 X and OpenMPI. As you can see here, because of that, our rendezvous protocol, we are able to do even better compared to OpenMPI here within the node. Similarly, if you see the collectives, like a broadcast and all, we are able to do better than this is a log scale. All these things. So here, especially the bcast is a log scale, so we are able to do far better. So here again, some more collectives. As I said, the collectives play a very big role when scaling the applications. So here, this is like within the node, I have 40 ppn, like there are 40 cores. So we are comparing the performance. Here is the all reduce. As I said, that is very important. So all reduce, and then here it is reduce. As you can see, we can deliver you compared to Spectrum API, we can give you like a factor of 2x, factor of 3x improvement. Now, the same lines along the collectives, Mellanox has something some of you must have been hearing called in-network computing. Okay. So what is in-network computing? So broadly, the earlier numbers I showed, over the network, you do point-to-point communication, and then I build some kind of an algorithm. Okay, let's say I want to do a broadcast. I can go through a tree, I can go through a binomial tree or binary tree. There are a lot of different algorithms to do. But now Mellanox is trying to take it to the switch level itself. That means the way the switches are connected, if I send data at one point, the switch itself is trying to broadcast it. Okay. Or the switch itself is trying to do reduce and all reduce. So within the switch, now they have actually mathematical components or a ALU logic, so which can actually perform this kind of operations. So what we have done, we have been following that trend. We have done a very tight integration of that technology they call SARP. So we have actually done a very tight integration of our MVAPICH2 library with the SARP. And these are the numbers, some of the numbers, which is taken on the Texas Advanced Computing Center. That is the largest InfiniBand system in the world. It has very close to 8,000 nodes, 7,861 nodes of InfiniBand. That is a production system. MVAPICH2 library is extensively being used there for all the applications. So here I'm trying to show just all reduce. As you can see, compared to the pure software-based solution, as I indicated earlier, with our tight integration with the SARP, we can actually reduce this MPI all reduce time by factor of 5, factor of 9, factor of 6 kind of things. Again, in many of the slides, I'm actually adding where all these papers have been presented and all. So those of you who are interested can actually take a look at this in more detail. So now that is for like a short messages. So now there is a newer Mellanox NVIDIA is going into a next level, which is coming like a SARP 2, or they call it SARP Scalable aggregation concept for large messages. So then again, we have done a very tight integration with their support, and as you can see, this version is not released. That will be released very soon. With the newer mechanisms, we are able to reduce even this the all reduced performance by factor of 3, by factor of 4, depending on the different number of nodes. Same thing here also, the MPI reduce, that is another collective. Even here we are able to improve it by almost factor of 16. Okay, so all these things, again, it is a research. We carry out these designs and then gradually we push into our releases so that the end users can actually take advantage of these. Now, this is a different concept called data type processing. So a lot of scientific applications, and even these days, a lot of deep learning applications use vectors, tensors. Okay, so that is called data type. So that means the data is not contiguous. Okay, so in your memory, data could be sitting at all different places. So you are trying to access them through vectors. You are trying to access them through some tensors. So here we have proposed a lot of optimization. In fact, this paper will be presented at HighPC, that is the conference in India, just in 2 weeks. We'll be presenting. So compared to all other libraries, as you can see, like Intel MPI here in our older MVAPICH2, our proposed one is like, in fact, can give you 35% better time. Okay, so if you have an application, like in this case, mini host, there's a mini app. We evaluated, but if you have an application which is using a lot of data processing, you can actually utilize our library to get a better performance. So here we are comparing, these numbers are again taken on this EPFL system because they have this neuron application that actually uses a lot of data type processing. So using our optimized stack, here this is this MPI is from HPE, that is like a commercial stack, whereas we're able to give almost 36% improvement in their actual simulation. And this was run on 9,000 cores, 9,900, very close to 10,000 cores. So we are able to improve the execution time of the application by 36% here. So these are like this, just some sample designs and numbers, just to let you know how we have been carrying out this research. But if you're an end user, you just need to download our stack and then run it. Okay, and you will be able to see very similar kind of performance benefit what I've been mentioning here. So then I'll try to introduce 2 additional concepts. That is all the CPU designs I've talked to you earlier, but there is a newer technology called DPU has come, data center processing unit, and of course the GPUs have been there. So I'll try to touch our designs with those DPUs and GPUs. So this data center processing unit is a very novel concept, what is coming. So typically, if you see, let's say this is your host, Then you connect a network like an InfiniBand. Typically, it has InfiniBand like used to have RDMA. It didn't have any additional intelligence. So now what has happened, this data center processing unit, they have actually provided some ARM cores on the NIC itself. Okay, NIC is the network interface card. So now you can think of some processors are actually sitting in the network card. So I call it like an executive secretary paradigm. Okay, so just like in any companies or any organization or in universities, you know, there are a lot of executives. There are also a lot of secretaries who are helping the executives. Okay, so a lot of tasks can actually be offloaded to the secretaries depending on their qualification. So very simple example, let's say I want to, just like this conference, let's say the Zoom had to be set up. It can be offloaded to a person saying, okay, you set up this Zoom, do everything and send me a pointer. Okay, the executive can do it. But then if the executive can do, then the executive will not have time to actually do his or her task. So then you offload. So we actually trying to take a similar concept. We try to ask the question how we can redesign an MPI library to take advantage of these DPUs, okay, using this executive secretary paradigm. And especially now the concept is just like I said, offloaded. So once you offload, it actually benefits the parallel computing. That means you can do overlap. Okay. So very simple things. Many times you would have seen, let's say take a real life example. You have a friend and Friday evening you want to go for a movie. So you tell your friend saying, okay, come to my house and then I'll go. Okay. So then there are two alternatives. Either you just sit and continuously wait for your friend to come. That means you are not doing any work. And as the friend comes, you can proceed. Or while your friend is on the road, you are actually trying to do some work. Okay. If you can do that, you will actually overlap your computation with the communication of your friend coming to your house. Okay. So that is the paradigm we have taken here. And I'll try to show some numbers here. Okay. So this is actually a design which is already available. We have presented recently at the ISC conference this year or earlier this year. So I'll take one concept of all-to-all, okay, non-blocking all-to-all. This is a very dense communication in parallel system. If you are trying to do all-to-all, that means everybody is sending data to everybody else. It's a very complex communication, okay. And over the last 20 years, people have come up with a lot of different algorithms to optimize. Okay. But all those things have been blocking. That means I do computation, I do all to all, and I wait for the results of this all to be available, and then I proceed. Okay. So while all to all is happening, the processors or the executives are not doing anything. They might be helping with the communication a little bit, like copying data from this buffer to that buffer and sending it out, but they are not truly doing computation. But now if I can offload those to our ARM processors or to the executives, I am totally free. Okay. So I can actually perform computation. And here it is trying to show. So we have the basic MVAPICH2. Now we have a new library called MVAPICH2 DPU. Okay. And now you can see the green bars are almost 100% overlap. Okay. With MVAPICH2, you see the below. These are like red, only 2%, 3%. That's the maximum overlap you can achieve. But now you can actually get 100% overlap with this new design. So that is the overlap. But now let's run this all to all. But this is a non-blocking all to all. What do we want to measure is computation plus communication, because that is the goal. It's not just the communication. Okay. So now if you see, the basic MVAPICH2 was not able to carry out that overlap. It is exactly on the same hardware, even with the DPUs, but the components were not redesigned. Okay. But once we do the redesign, you see your all to all is running 22% better, 17% better. And this is running on a 32 nodes, 32 ppn, like 1000 process. And here it is a 512 process. Once again, I'll say this is exactly the same hardware. So the question is, can software take advantage of the new mechanisms and features available in the hardware? If you can do that, your job, a parallel job, will be running much more faster. So then that was only at the collective level. So actually then the question is, okay, really my application can be accelerated. So we took an example of a P3D FFT application. Okay. So many scientific applications actually use this FFT. So here we worked with the developer from San Diego Supercomputing Center who has designed this P3DFFT. And here actually we worked with the application developer to reorganize the code. If you remember my example earlier, if your friend is coming and you are not doing anything, then you cannot really overlap. Okay, so that means I need to change my mode. Okay, so that's what happened. We worked with this application developer. So the application developer was able to do some computation, initiate non-blocking all to all, and then do some computation. Okay, so once we did that, and then we evaluated with our DPU. So this is an application benefit. See here, 18%, 21%, 12%, 14%, depending on the grid sizes. Same hardware, we are able to accelerate by 21%. Okay, so this has been actually continuously. Now we are going with more and more collective operation. Another is called I-all gather. Now you can see benefits. You get like a 41%, 48%. Broadcast, even benefits is higher, 59%, 50%. So all these actually being available now. So this is where I'll introduce a little bit about the Excel solution, that commercial spin-off I indicated earlier. I'll come back to that even in the end. So this is being developed through a funding from United States Department of Energy to really take the MVAPICH2 library and then trying to optimize that for the DPU. Okay, so this is the MVAPICH2 DPU library. Currently it has all-to-all, I-all gather, IBCAS. So whatever the numbers I showed, if you have a DPU cluster or a cluster with the Mellanox/NVIDIA DPU, you should be able to directly accelerate your applications like this. So we are also trying to show another another collective. We are trying to take iScatter. We have got these kind of results that will be available in the next DPU release. Okay. So those are all the DPUs. Now let's try to go to the GPUs, okay? Because GPU also brings a lot of excitement. How we try to put it together, the systems. So if any one of you have done GPU programming, many times you would have seen, let's say this is a CPU connected with a GPU and then InfiniBand network, like these are two nodes or like a 4-node cluster, you are connected with InfiniBand switches. Typically GPUs, you try to push the data there and some kernels you launch and then computation happens. But then the question is, how do I move the data, the result from one GPU to the other GPU? Okay. So typically people do a CUDA mem copy, then they do an MPI send, and then you do another MPI receive at the other end, and then you do a CUDA mem copy so that the data moves from GPU to GPU. This used to be the practice for many, many years. Now if you do some analysis, when we started doing some analysis, we saw that it is good for the end programmer, but performance is very, very low because it goes through 3 copies you need to do. Okay, so if you are sending a large message, the latency is really huge. Okay, of course, if you are some advanced users, they know CUDA programming and all. What they do is they try to do a little bit of pipelining. Okay, so that means instead of sending the entire data at the same time, you see the animation, you try to do pipelining and then keep on sending the data using CUDA mem copy async, do an MPI iSend, which is non-blocking, and then in the receive, you do a similar kind of pipeline receive and you do the same. With this, you will be able to get better performance, but the productivity is low. What do I mean by that? The productivity is, let's say you are an end scientist, you might be a chemist, you might be a material science engineer, or you might be an economist. Instead of you focusing on your science, you are trying to understand what CUDA is, read all the CUDA programming, what MPI is, what is MPI blocking, non-blocking. You spend a lot of time to really extract performance. Okay, so that's why we say that this is not a very productive approach. So we ask the question that can we come up with a intelligent MPI design, okay, so that the solution will be high productive and high performance. So we introduced this concept called GPU aware or CUDA aware MPI. Some of you might have heard of this. We actually did this in 2011. We had a paper at ISC. In the last 10 years, all other MPI libraries, everybody has picked up this concept. So now you see multiple libraries have CUDA aware MPI support, even TensorFlow, deep learning, everything. But we started this almost 10 years back. So the idea is that just like you do an MPI send receive from host memory or host buffer, you just do at sender side, you say MPI send device buffer. You just give a buffer from the GPU sender side, and then say where to write. And everything else, as you can see the animation, everything is else taken care by the library, MPI library. Okay, the end users don't have to do anything. Okay, and that will lead to really high performance and high productivity. Now, if you put it together, I mean, there are a lot of, I am just introducing this concept, but of course, I mean, we carried out almost like 2 years of design together with NVIDIA, Mellanox. That time they were separate to bring these solutions together. Look at this number, 1.85 microsecond. If I have 2 GPUs on 2 different nodes, not on the same node, I'm able to send the data from one node to the other node in 1.85 microsecond. Okay, that is the kind of the best performance you can see from any other MPI libraries. Not only you see the latency improvement, you also see bandwidth improvement by factor of 9x, factor of 11x. That is on x86 platform. The same thing happens also on the Open Power platform. So these are numbers are taken from Summit/Sierra kind of system here. So here, if you see intra-node, GPU to GPU, within the node, 2 GPUs are connected. In 760 nanoseconds, we can actually send the data from GPU to GPU. And then bandwidth wise, if they are connected with NVLink 2, this is connected here, we're able to saturate almost like a 65 gigabytes per second. And internode, this is an open power platform. This overhead is a little bit higher. We are able to send data at a 2.18 microsecond instead of 1.85 as I showed earlier. And this is 2-port EDR. We are able to get like a 23 gigabytes per second. So those are like for NVIDIA GPUs. And now we have taken the same design for AMD GPUs because AMD GPUs are just coming into the market. So very similar things here we have done in our latest MVAPICH2, that is the GDR version I indicated, GPU Direct RDMA library. Here we are comparing with OpenMPI, very latest OpenMPI numbers. As you can see, we are able to deliver lower latency and the bandwidth, we are able to give even higher bandwidth, both for intranode and internode. And so if you put all these things together, let me show you some application level numbers. So here you can see this is like a HUMD Blue. This is a molecular dynamics application. You can use the basic MVAPICH2, which doesn't have the CUDA support. CUDA aware MPI support. But if you have the CUDA aware MPI support, now you see your boost your performance. This is like average time steps per second. Like higher is better. I can actually give you almost a factor of 2x improvement. So then very recently, we have gone even one step further. No other MPI library has these designs yet. This is called on-the-fly compression. Okay. So now think of earlier, like let's say you have done some computation in the GPU. We just send the data. But if the data is very large, it still takes time, even though we use a CUDA aware MPI. But since the GPU has a lot of cores available, can we do compression? And this is on-the-fly compression. That means before I send the data, I actually compress and send it, and the other end I do uncompress and receive it. Okay. Of course, it depends on the data characteristics, different applications, what kind of data they are sending. So here we brought that design. This was actually a best paper finalist at IPDPS conference earlier this year. We presented, and we took an application. We worked with this application people. It is called AWP ODC. It is a earthquake simulation. You remember I showed an example earlier. So we actually work with these people. So at that simulation, this is happening with the 512 GPUs. The overall throughput of this application, we are able to improve by 35%, 18%, and reduce their execution time by 26%, 15%. Okay, so the idea is that if you use our MVAPICH2 GDR library on your system for your application, we can give you much more higher benefits compared to any other library. Okay. Similarly, this is another example which is running on the Summit Open Power System at Oak Ridge. This has been done by other people. They presented we carry out an annual MVAPICH user group conference. They presented in this conference. So here you can see they are compiling Spectrum MPI, MVAPICH2, Open MPI. So UCX now MVAPICH is able to give them very good performance. Okay, we are actually working with them. In fact, to take the compression and all other advanced things, and might be in the near future we'll see even better numbers here. So those are like the commodity systems. Let me show you some numbers on DGX. So NVIDIA has currently, many of you know, they have this DGX system. They're calling it as an AI system. Okay, and with that they have the library called NCCL. Okay, NVIDIA Collective Communication Libraries. I'll show you not only these results, a lot of other results. We are able to actually beat and deliver better results than the NVIDIA's collective communication libraries. Okay, because MVAPICH, just like an MPI library, we have been optimizing all these collectives for years. Okay, so here if you see, this is like a all-to-all. As you can see here, small size and large size, we are able to significantly give benefits. Okay, and this has a lot of implication not only for HPC application, like here we are seeing this HEFFT. That is like the Oak Ridge people have been doing high performance FFT design, as you can see, compared to this is the higher the better performance. In terms of gigaflops, we are able to give them far better performance. But we are actually working with some of the vendors. I don't want to say now. There's a lot of recommendation models are being worked out. And those recommendation models are actually, they use all-to-all. Okay, so if you can optimize all-to-all on GPU system, all your recommendations model get a big boost. So we have some papers in the pipeline, and many in the near future you will see. Even we can accelerate through these designs all these recommendation models. So this is another use case, the weather forecasting. Just like you know, I mean, any country these days in the iPhone app, you see the weather. We have been working with Switzerland Supercomputing Center. So if you have been to Switzerland for the last 4 years, or if you plan to go there, the actual real-time weather forecasting is coming from our library. So we have a 3-year collaboration going on between CSCS, that is the Switzerland Supercomputing Center, and Meteo Suisse, which is the weather forecasting office. And we, by using MVAPICH2 GDR, because a lot of these applications, they use all those data types, CUDA-aware, all those concepts. When you put it together, your application starts running much more faster. And here you can see with 32 GPU nodes, we are able to give them like a 2x improvement. On 96 GPUs, almost 30% improvement. And that really gets translated into cutting down your weather forecasting execution time. We work with a lot of national labs. This is an example of Idaho National Labs. They are one of the in US. So they are a very large house. They do nuclear energy simulation. And all the entire simulation is totally driven by MVAPICH2 library. So they use a lot of these other packages called Moves, PETC. They actually gave a talk again in August in our annual MVAPICH user group meeting. So please feel free to take a look at this. So these are just some high-level ideas of just to introduce the MVAPICH library to tell you what is inside, okay, and how that actually try to translate to the benefits in terms of performance and scalability at the application layers. Are there any questions for this part? Okay, so if not, let me move ahead. So next, I'll try to focus on the deep learning machine learning. You remember, like I gave a lot of examples earlier, applications, but how do we really deliver performance to them? So what are the major challenges? So once you have this kind of this deep learning, machine learning, a lot of huge data is there, you have to run different models. You need to have good scale up and scale out. So that means, what is scale up? That means within the node, if I keep on adding more number of cores, more number of GPUs, I should get higher and higher performance. Okay. And then the question is scale out. if I have more number of nodes, like those examples I gave, like a summit has 4,000 nodes, how do I really scale to 4,000 nodes? Okay. So in this context, there has been a lot of work has happened over the years. They're using all the different underlying communication libraries. Okay. Traditionally, TensorFlow started with gRPC. Sometimes they do Hadoop. NVIDIA has been focusing on this NC nickel. End goal is here. We want the best scale up and best scale out. So what I'll try to show what we have done.
Panda sir, sorry to
Yes, yes,
interrupt. There is one question which is very
yes, yes,
relevant to the topic that we are discussing. Are you
yes, yes,
considering porting these techniques to work with FPGAs2?
yes. So that is a very good question. So the answer is we started actually once 2 years back. We worked with a FPGA company. The currently the what we showed there, the still the FPGAs have a lot of overhead in terms of programming. Okay. So that is because FPGA, as you know, that means it's a field program, you will get arrays. So if, when you try to do MPI offloading, it takes some time for it to be programmed. So the question is your application can tolerate that? Okay. So when we did with these people, we had actually 1.5 year collaboration with them. We are able to improve without that programmable time. Okay. So to the best of my knowledge, as we see a lot of FPGAs companies, the overhead is reducing, but it's not that very good yet. Okay. So that's why it is still on our radar. After that collaboration, we have not jumped in yet. But if any one of you have a good FPGA product where this programmability will be much more faster, we can actually explore that. Does that answer your question? Okay, thank you. So here, so what I'll try to show what we have done is this through our MPI design. So what does that mean? So let me put this very broad challenge saying we are trying to look at the scale up and scale out for the deep learning and machine learning frameworks in these heterogeneous resources. So I'm sure some of you might have heard of these terminologies, okay? But let me explain. So a lot of these current machine learning, let's say, or the deep learning, people use TensorFlow, PyTorch, MXNet, etc. And then a lot of middlewares are coming here. There's a torch distributed deep speed. So what we have done, we have linked, let's say, the Horoword or torch distributed deep speed to our MPI library below. Okay, so we have a project. This is the high performance deep learning project. We have a very detailed user guide. You can actually download our stack. So we have linked MVAPICH2 and MVAPICH2X for CPU training and MVAPICH2 GDR for GPU training. Okay, so you can actually do training on either platforms. I'll show you some numbers. And in this case, what happens, your end users, they don't get disturbed. They can still use their TensorFlow level. So they don't need to learn anything. It's the system developers or integrators can actually try to put it together. In fact, later on, I'll show you from a commercial perspective, from Xscale solutions, we have a much more even better solution. Even you don't have to spend any time. You can just download our package and it will run, okay? And give you far better performance. And then the end users can directly run their TensorFlow PyTorch applications and see the benefit. So that's what I call it, like MPI driven solutions, okay? So let me try to, with that kind of a solution, let me show some numbers with data parallelism, model parallelism, hybrid parallelism. I'll also try to show some numbers with the digital pathology I talked earlier, and then I'll go into the machine learning applications. So here, first I'll try to start with CPU. Many times I know whenever people call deep learning, people always think of GPUs, but GPUs, as you know, are still expensive. Okay, so using our stack, if you have access to see a CPU system, you can still do deep learning. Okay, it may not be very fast, but you can still utilize it. So here, this is the distributed TensorFlow. We ran it on the TACT, that is the Texas Advanced Computing Center. So this was running on 2,000 CPU nodes. And each CPU node has 56 cores. So altogether it is 114,000 cores. Okay. So now if you see, we're able to deliver very linear performance. You see, the MVAPICH2X is getting very linear performance, very close to the ideal. And this is a linear, the exponential log scale. So effectively it is like exponentially increasing. And here if you see the ResNet 50, we're able to train it on this system in 7 minutes. Okay. So it can be done. So if you have actually access to any CPU cluster, many times people say, no, we should go for GPUs, but you can actually utilize the CPU clusters to carry out your training. Now, of course, with GPUs, you can actually do better. These are the numbers I'm trying to show from the Summit system, which is the number 2. So here we are trying to do the ResNet 50 training with ImageNet 1K. It has 1.2 million images. And here we are able to scale. This is comparing with a nickel. As you can see, we are able to scale up to 1500 GPUs. These open power platforms with InfiniBand, we're able to scale and deliver better performance. In fact, the nickel-based solution, when we ran these experiments that time, didn't even scale beyond 384. Okay. Now they have improved. They are able to go higher. But overall, you can see like in just 4.5 minutes, we're able to train this ImageNet 1K with 1.2 million images. So here it shows the strength of our solution, which is purely MPI driven. You don't need any nickel or any other libraries, and you will be able to get this kind of performance. So we have done very in-depth testing. This is the Livermore Lassen, that is also an open power platform in the Lawrence Livermore National Lab, with all these different middleware, the torch distributed, Horobot, and deep speed. Compared to like these numbers are with nickel, the green numbers are with MVAPICH2 GDR. As you can see, steadily using the MVAPICH2 GDR as the communication backend, we can give you almost like a 10,000 images per second faster. Okay, so that means you will be able to reduce your training execution time using our solution. So that is with pure data parallelism, but gradually, as you know, the data sizes are increasing, the model sizes are increasing. Here, I'm just trying to show an illustration saying as your input message sizes, image sizes increase, everything cannot fit within a GPU because GPU has some limited memory, like a Pascal, Volta, even the CPU, even the A100. You take any one of them, beyond certain, if your model size is very large, you cannot do data parallelism. So this is where the model parallelism comes in. So what we have done, not only we have gone with the model parallelism, we have actually designed a hybrid parallelism, which can take advantage of both model and data. So let me show you some numbers. So this is the hybrid parallelism. We presented this paper at ISC 2020. It is also available in the archive. You can download and take a look. So this one, we used it on 512 nodes of the TAG Frontera. And here you can see we were able to get almost 481x speed up and with a very close to 94% efficiency. So that means this hybrid parallelism can actually run on this kind of CPU-based system. And then it can also run on the GPU-based system. So these numbers are taken on the Lawrence Livermore Lassen, which is again an open power platform. So this paper was presented last year at Supercomputing 2020. So here we are able to scale to 1,000 GPUs and using multiple replications. These are different models, but if you see the end number, that's the green line, we're able to get an efficiency of 97% on 1,000 nodes. So that means we're able to keep all of them busy all the time to get that kind of speed up. So then we have moved to the next one, that is like the traditional ResNet image kind of things, but now we have gone into not just data parallelism, hybrid parallelism, model parallelism, we have gone to subgraph parallelism. Okay, and for example, like if you have a your DNN architecture like this, how do you map it into multiple GPUs? So that's what he's trying to show, how effectively you can do the mapping so that you get the best performance. So that's what we call like a subgraph parallelism. And this was also presented at the IPDPS earlier this year. And with that, this was again on the Lawrence Livermore Lassen system, which is open power with InfiniBand. We are able to scale up to 1,000 GPUs compared to the data parallelism. This is the, if you see the subgraph parallelism, we are able to give you almost factor of 3 improvement. Okay. So then putting all these things together, let me take this example of the pathology as I indicated earlier. This we have been working with some of my colleagues, the pathologists at the Ohio State University. These pathology images are very large. Okay, each Each one, they call it like a whole slide image. It has 100,000 by 100,000 pixels. Okay, you cannot fit everything into a single GPU memory. So most of the times what they do, they create some tiles and then do the deep learning on top of them. But once you do this tiling, you lose a lot of information at the edge, okay, which are very important. So what we try to do, we try to work with them to see whether we can deliver a very high performance solution from them. So we try to bring HPC and deep learning to the pathology. So when they were working there, first we started with one node, one GPU. I'm not showing the number. It was taking them 32 hours for training the entire set. We first did a scale up. You remember the scale up I said earlier? So within a node, most of the time these days you see 4 GPUs. So we are able to work with them and reduce that to 7.25 hours. So then we continuously improved our solution. We reduced even to 4.21 hours. And then we are able to do the scale up. So now we got up to 128 GPUs. We reduced their overall training time just to 0.46 hours. So we're able to give them like a 15x reduction in the training time, and their throughput speed up was almost factor of 22. Okay, so this shows a very clear case where we can really take all the research, whatever we talked about, MVAPICH2 library, high performance, deep learning, everything being put together into for a single application. In one of these applications, really trying to show the impact. Similar things we have now started doing with the machine learning. I introduced this concept earlier. If you machine learning, if some of you are familiar, there are supervised learning, unsupervised learning, reinforcement learning. So all these things are being pushed now by NVIDIA through a library package called QML. Okay. But what NVIDIA has been proposing, the QML, they have the support of their underlying Nickel library, and there is a communication stack called UCX. They have only support for that. So what we did is we tried to, so that means if you want to run QML, you need to download UCX, you need to download Nickel and then run those things. So we tried to go through our MPI route. We introduced one module called MPI for Pi. Okay. And then we linked it with our communication backend with the MVAPICH2 GDR, because MPI is already doing that communication. So that is always the backend we want to use for all these applications. So we have actually made a release earlier this year. If you are running QML applications, you can download these from our site. Now let's take a look at the number. So these are all the different, like an application like k-means, nearest neighbor, truncated SVDs. These are the standard benchmarks in the machine learning domain. And compared to using the Nickel library, now if you use the MVAPICH2 library, see the speed up. We can give you almost 1.6, 1.6, 1.3, 1.4 kind of speed up. Okay. So hardware remains the same. It is a question of software. Okay. Which software you use and which library you use, and that will determine the overall impact you can see at an application level. So any questions on the deep learning, machine learning parts? Okay, there is a question in the chat. Let me see. Tiling. What if the algorithm is done in multiple iterations, with each iteration slightly translated to the left, right to overcome the loss of edge situation? Yeah, this is exactly, these pathologists were trying to do that. Okay, but as you can say, this iteration, and because you need to do additional computation, all right? Your solution will work. That's why it was taking them much more time. Okay, so if you can actually have a better solution like the model parallelism or hybrid parallelism, you will be able to actually make it faster. Okay, so that you don't need the tiling, and that was our actually the end solution together with our scale up and scale out. Okay, so let me then go to the big data side. I introduced the big data. A lot of different stacks are being used. So this is a project also running for many years now. So if some of you must be familiar with Spark, Hadoop, Kafka, HBase, Memcached, all these are like the big data software stack. So earlier, these stacks were, if you download from Apache Spark or Apache Hadoop, they always run with TCP/IP at the bottom. And of course, if you have an InfiniBand cluster, InfiniBand has something called a IP over IB. That is a module, like a kernel module. So you go through your stack, and you can run it over InfiniBand, but you don't get the good performance. So over the years, what we have done is we have actually done native design over InfiniBand bursts. That is like a really coming to the lowest layer, and all these stacks are available from this big data high BD site. As you can see, there have been like more than 40,000 downloads here. 340 organizations have been using it. So let me take one example, okay, just the Spark, and see what we have done and how much benefits you can see. So traditionally what happens, if some of you are familiar with the Spark stack, typically they have this Java sockets interface. Here, that is traditionally it runs over Ethernet, or it can run over IP over IB. What we did is we actually modified the software stack. So within this JNI, Java native interface, we actually put our RDMA based communication engine. Okay, so this has not been linked with MPI. This is a very different project. Now we are actually integrating with MPI. I don't have those results yet. We have started getting some numbers. Might be another 2 months. I'll be happy to share those numbers. But this was done very differently. We tried to put some RDMA based communication engine design there. So now if you take a look, this is like a RDMA Spark. This is like a page rank, which is a very common application or benchmark there. All the same InfiniBand hardware. Okay, so this is a 768 core experiments. This is 1536 core experiments. We are able to reduce the execution time by 37%, 43%. Okay, because we have done the native design. Okay, so we don't go through the communication protocol overheads. We try to cut all those things down and then accelerate the application. So now this is another, so that is at a benchmarking level, but this is actually, we work together with San Diego Supercomputing Center. There is an astronomy application. It was using the Kira toolkit. This was a little bit earlier. This was a paper in 2016 when the field was, excuse me, coming up. So compared to the Apache Spark, which was using IP over IB, using our RDMA Spark, we are able to improve by 21%. Overall execution time, we are able to accelerate. So now what has happened? So these stacks are already there, but the field is changing. So we are also adapting to the field. So there is a newer, especially this deep learning, machine learning, and big data has been combined with a new field of data science. Okay, so that's what we are trying to address it now. And in that data science, there is a newer middleware which has come up called Dask. I don't know if some of you heard of it. If not, you can take a look. So the Dask, this is being pushed by NVIDIA, and they have two solutions. They had two solutions. One is the TCP/IP you can run, or they go through their UCX software stack. So again, with keeping with our storyline, we wanted to use our MPI library as the backend. So we introduced, earlier I said we introduced MPI for Pi for QML. Here we introduced a similar module called MPI for Dask. Okay, so now what happens? You can directly use the MPI backend. Okay, so if you have MVAPICH2 GDR installed on your system, not only you can do your HPC application, all the machine learning, deep learning, now you can also do data science applications. So here again, we have made 2 releases earlier this year. You can actually now run this Dask on both CPU-based system as well as GPU-based system. Let's take a look at some of the benefits what you can get. So here again, I'm trying to show some benchmarks. This is the benchmark one. As you can see, the lower is better compared to IP over IB or UCX. They are running on exactly on the same hardware. We are able to give almost like a 3.47 benefit, or even factor of 7 benefits here with these benchmarks. These are the another on the GPU based systems. Here we are able to give almost factor of 3, factor of 2.9 benefits. Okay, so again, you can take a look at this more details in the papers. If you have if you are using Dask, please feel free to download our stack, and you should be able to again get similar kind of benefits. So now you can actually mix and match a lot of these designs. Earlier, if you remember, I introduced GPU on the fly compression. I only mentioned about scientific applications. Now you can use that also for Dask. Okay, because since we have the MVAPICH2 GDR as the common backend, I can use all those features for different software stacks. So here we studied, this is on the Dask benchmark, creating the QPy array and distributing it to the Dask workers. You can see we are able to give you 1.56x higher throughput and almost like a 37% better execution time. Okay. So as these solutions are coming, so far I have only indicated like on-premise systems, but gradually we are trying to push these solutions to the cloud. So we are working with all the three major cloud providers: Azure, AWS, and Oracle. So in the Azure, already MVAPICH2 is included. Over the years, we have worked with them. So if you, for example, MVAPICH2 236 is the latest release, it's already included. If you have an Azure account, you can directly go to this link and use our library. So that means if you have an application which you are running locally, compiled with our MVAPICH2 library, the same compiled version can directly work on the cloud also. So here I'm trying to show some numbers on their latest ND A100 instance. So this is the AMD systems with Ampere A100 GPUs. We give same performance like what I indicated earlier. This is the MVAPICH2 GDR. We are able to see the bandwidth, GPU to GPU intra-node. We are able to give like almost 133 gigabytes per second, and inter-node, we are able to saturate the EDR, the speed. Now with AWS is a little bit different story. AWS actually doesn't use InfiniBand. Azure has gone InfiniBand. So that means whatever we produce, all our software stacks can directly run over Azure. There are no issues. Okay. But AWS has their own adapter called Elastic Network Adapter. Okay. They changed the name a little bit. Later on, they say Elastic Fabric Adapter. Earlier, they had Elastic Network Adapter. So they have over the year, they have actually improved their adapter. So they have followed a lot of InfiniBand principles, but they have introduced a new transport type called SRD, Scalable Reliable Datagram. Okay, InfiniBand doesn't have this. InfiniBand has the on-level datagram, but now they have done a scalable, reliable datagram. So then what we did, we actually worked with them and we have come up with a optimized version of our MVAPICH2 X with their EFA adapter. Okay. And we have made a public release. It is available from our website. So if you have an AWS account, you should be able to download our stack and then use it. So now we are comparing. This is their latest ARM instance, Gravitron instances. So we are comparing with the latest MVAPICH2 with OpenMPI, see some of the collectives, all reduce and scatter. We are able to deliver, and then the y-axis here again is a log scale. So it may look very small, but this is a huge gap we are able to do. But this is a very interesting result. So since we have gone to the lowest level of the hardware, the other libraries have actually gone through something called a leap fabrics. Some of you might have heard of. There is another middleware which is being used these days. It's a competitor to UCX. Intel and NVIDIA are competing against each other. But since our design is really low, as you increase the number of processes, we give you the best performance and scalability. Okay, so see up to like a 36. These are 36 cores, 1 node, 2 node, 4 nodes. You don't see any difference. But as you start going to 8, 16, and more number of nodes, see the performance gap. So this is for the weather forecasting application, which is a WRF, which is very common. People run it on the cloud. Now you can see. It not only this execution, reduced execution time, actually try to translate into real money. Okay, many people don't correlate that, but in a cloud environment, that directly relates to the money, cost saving. The same hardware, if you are using another library, it might be taking you more time and you are paying for that extra time. Whereas using our library, you will be able to get the same result much more faster. Okay, and then you can actually try to cut down your cloud budget. Okay. Then recently we have worked with Oracle cloud instances. So here you will see the same. I'm trying to show some numbers: MVAPICH2 X versus HPC X. That is a Mellanox proprietary software stack and Intel MPI. As you can see here, we are able to give you 2.7x better, 21x better kind of things. Okay. And by the way, the Oracle Cloud actually uses Rocky, which is the RDMA over conversion enhanced Ethernet. So all these three cloud providers have gone three different directions, but we have been working with all of them to have customized solutions for each one of them. So with this, let me try to conclude. I think I have another 8 to 9 minutes. So all this research, these are happening from the Ohio State side. We have all these results, publications, and also all the software stacks available. But as more and more people have been using for the almost like many years back, people continuously ask me questions saying, can people get commercial support? Okay. That means just like any other software library, if any organization or an HPC center really wants to purchase a license, okay, so that if any issues come up, they can contact us. We can fix those for them. So this is where this commercial spin-off called Xscale Solutions started. Okay, so it started in 2017. Now in the last 4 years, we have been actually providing a commercial support to a lot of national laboratories and international supercomputing centers. So here, for any given, like even though commodity clusters are there, every cluster is different. It's within MPI library itself, there are almost 300, 400 parameters to tune to get best performance on a given platform, and also for all different applications. Okay, for a given application, if you have a killer application and you want to really see the best performance, one has to really go through a lot of performance profiling, performance engineering, and adjust all those numbers, and you will see better performance. Okay, so those kind of services we actually provide through this commercial spin-up. But gradually, as that has picked up, people have started asking us more value-added products. So that means whatever is available from the OSU side, they want some more features. Okay, and some of them may not have a lot of research values, but these have a lot of commercial values. Okay, so we have been expanding along that direction, and these are the currently we have 4 value-added products. I talked about this MVAPICH2 DPU earlier, but let me touch a little bit about these 3 other products. So the Xscale HPC is very similar to MVAPICH2 library. Okay, plus the commercial support. Okay, so that means for a given platform, it is fine-tuned for all the different platforms, x86, OpenPower, ARM, GPUs, NVIDIA, AMD. And through this, actually, we can work even with the integrators. If you are the end user, we can directly work with you, or if you are purchasing a machine from some vendor, we can actually work with you. All these kind of things are not possible from the Ohio State University side, because that is purely focuses on research and development. But from a company side, we can actually work with any of the end users or organizations to really deploy systems like a software stack. But this is a very unique product, what we have done, which is not available from the Xscale AI. So it is built on the same principle I showed you earlier, like the high performance DL. That means it is an API driven library. But we have a lot of additional optimizations. I'll show you some numbers in the next slide. But in addition to that, we also provide some profiling and introspection. Okay, so let me talk about that in the next few slides. So this is the very latest numbers what we have done. So this is like as you can see, even with the 16 GPUs, the Xscale AI, the traditionally what people have been using, the standard Horrowboard and the nickel-based solution, we have an optimized, and this is in fact better than even the OSU side solution. With 16 GPUs, you think of like a ResNet 50 training, we can accelerate by 26%. Okay, so you will be even get better return on your investment with using this kind of packages. So then what we have done is, many times when you run some deep learning application or machine learning or even data science application on a GPU cluster, you are not sure whether you are getting the best performance or not. Okay, your application will run, but the question is, are you getting the best performance? So what we have done a very in-depth profiling, coming from the TensorFlow layer, going through Horrowboard, going through MPI, going even to the InfiniBand network. We have developed this kind of a dashboard, just like in the car. While you are driving the car, you know exactly how speed you are going, what is happening, mile consumption, all those things. So everything you can see it at one place. So here it is actually trying to show, for example, like I'm running ResNet 50, the total time in all reduce, this much time is taking. It gives you how many all reduces are called. It shows, look, This message size is most important to us. A lot of all reduce are being called here. It shows the all reduce latency is not smooth. That means the all reduce have not been optimized. So a lot of this information you can visually see and react to those, and then you can actually perform optimizations to boost your performance. Okay. So here, for example, I'll show you two use cases. We worked with some users. The user was running in this kind of a mode. Let's say it has 132 GPUs. They were only getting this much performance. Ideally, you should be getting this much. So we worked with them using the AI tools. Within few days, they were able to figure it out, what problem was taking place. And then after fixing those, they were able to get 30% benefit from their online system. This was another use case. Two similar things happened. It was running on a 1000 GPU system. The expected was 370,000 images per second, but they were only getting 181,000, only half of that. And they were not able to figure it out. If you really want to, in the absence of such tools, it takes sometimes weeks to really find out what is happening. Even though if you use NVIDIA's some of the tools, it will only tell you what is happening on the GPU. It will not tell what is happening in the network or even at the upper layer. So we have done this tight integration, and using our tool, we are able to give them 1.9x speed up, and came very close to the final estimated or expected images per second. So in that way, this xScale AI solution, so we are trying to target for all the deep learning, machine learning applications. It's a very unique product in the market. It is based on those MPI driven solutions, but it is better than the visual side solution, and it has these deep introspection capabilities, and is available for both OpenPower and x86 platforms. And then very recently, this is the latest product which we are working now, is called Checkpoint Restart. A lot of these deep learning applications nowadays, if you see, it takes days. Okay. And what happens if a machine goes down, or a GPU goes down, or a network goes down? You need some kind of a checkpoint restart flexibility. And some of the time, it might be happening, you are doing this deep learning, but some high priority job has come. Can you preempt? Can you preempt your job? And then let's run this high priority job and then get back your training. So this is where also you want to have the scalable checkpoint restart. So this is what the project we are currently doing within a funding from Department of Energy. The original scalable checkpoint restart library was developed at Lawrence Livermore. We are working with them in collaboration, but this is a enhanced version which is being targeted for exascale system. Let me show you some very initial numbers. So here it is running. This is a ResNet 50 training we have support for both Horovod and PyTorch. These numbers are with PyTorch. So of course the PyTorch has its own kind of a naive checkpoint solution, but that is not good. As you can see, this green line, the overhead keeps on increasing as you go into 128 GPUs. Almost you spend 50% overhead. Okay, because checkpoint, the way you write and then the way you get it, you are losing time. Okay, but whereas you see our SCR exa things, as you can see, we are able to give you almost like a within 10% overhead. This is for the Horovod, exactly the same story. Here you see your naive design is almost going to 55% overhead with 128 GPUs, but we are able to keep it very flat. So these are the kind of the value-added products we are designing, and gradually they will be combined so that you can, for your HPC AI deep learning application, you will be able to get the totally integrated and combined solution with commercial support. So it will be just like any other software stack you get from any of the big companies. So with this, let me conclude here. For the last 2 hours, I provided a very high-level overview. If you see the emerging applications, and anytime you need to design the next generation HPC systems and cloud, you need to have a holistic view of HPC, deep learning, machine learning, and data science. I provided a set of solutions, how we have designed this over the years, and how those things you should be able to utilize these, and that will lead to the very scalable solutions for the next generation exascale and zetascale systems. So with this, I'd like to thank all our funding sponsors. What I presented here in the 2 hours is a work of 20 years. So we have been able to sustain that with not only funding from federal agency, we get a lot of funding from all these companies, direct cash, so that we can actually provide support students, staff, and do all this development work, research, and then make the solutions available. But last but not the least, these are all my heroes. These are all the students, staff who have worked over the last 20 years. So every time I present a talk, I just want to salute them for all their contributions. So, so as we are moving, even though all these people, I have a very large group here, but we are continuously looking for bright and enthusiastic personnel to join from the OSU side, like a PhD students, postdoctoral researchers, or programmer, big data, deep learning, all programmers, software engineers. We also have a lot of software engineering positions available from the Xscale solution side. So if any one of you are interested, please feel free to send me emails at the appropriate, using the appropriate addresses. So with this, I'd like to conclude the presentation here. If there are any questions, please post it into the chat or directly ask questions. I'll be very happy to answer. Thank you.
Thank you very much, Professor Panda. It was really an awesome talk for the 2 hours, and you have just put on your 20 years of your development in 2 years, and I'm sure that we need to have much more sessions like this, and we need to have a continuous engagement with Ohio State University. So it will be great. We have something called as a semester abroad program, where our students will be visiting the foreign university for doing their final semester project, so that the entire to and fro fares are borne by the university. So it will be it will be great if we can send some students to your lab who can spend time.
We can always discuss this offline. We'll be very happy to talk. There could be a little bit some restrictions. I'll talk to you. Okay.
Yeah. We'll have the discussion offline. And thank you very much for the insightful talk, sir. And the HPC that we have built has all state-of-art A100, V100 GPUs, and if it is augmented with tools like MVAPICH, it is obviously going to be an add-on to the overall compute power.
Sure.
Ganesh, any inputs from your end? Ganesh, are you there? Yeah, so if there are no further questions, we'll just wind up the session. We'll just break for tea now. And within 15 minutes, by 11:20, I request all of you to assemble in the auditorium. And the next session would be on demonstrations on how to deploy deep learning ML applications onto the HPC. Yeah. Thank you, Professor Panda.
Okay. Thank you. Thank you then. Yeah. Bye.